equilibrium constant with our equilibrium expressions, but they do teach us a lot more several important factors about equilibrium. The equilibrium constant can tell us the tendency for the reaction to occur. So is it likely to actually happen or not? When we're given a set of concentrations or conditions, then when you plug it into the expression, does it actually represent equilibrium? Does it equal the constant that we saw for previously? And then also, we can predict whether or not the position will be achieved from a given set of initial concentrations, or where does the equilibrium position lie. So the K value, the equilibrium constant, tells us lots of information. In case you need some more information than what I'm telling you in this video, you can look in your textbook on those pages to learn more about this stuff. So the inherent tendency for reaction to occur is indicated by the magnitude of the constant, meaning that when K is greater than 1, the equilibrium position will consist mostly of products, so we say that the equilibrium lies to the right. So when K is greater than 1, we have mostly products, so the position is on the right because products are on the right side of the reaction. When K is less than 1, so it's a small value, that means that it contains mostly reactants, so the position would be to the left. Okay, so this is this information that you need to remember, that when K's values are very large, mostly you have products. When it's very small, you mostly have reactants. Most of the time, we progress to the products, so most of the time our K's will be larger. The size of the K and the time required for a reaction to reach equilibrium are not directly related. The time required depends on the reaction rate that we studied with kinetics, and also the activation energy required to overcome that barrier. K is determined by thermodynamic factors such as the difference in energy between reactants and products and other factors like that. So the K and time do not directly relate. It relates more to temperature than to time. So here's an example of a multiple choice question where we are comparing the value of K. At night, an equilibrium reaction between two different nitrogen compounds generates dinitrogen pentoxide in the atmosphere as represented by our equation that has a K of 2.6 times 10 to the negative 11. A mixture of nitrogen trioxide and a tenfold excess of nitrogen dioxide, meaning that the limiting reactant here is going to be the NO3, are placed inside a rigid container at constant temperature and allowed to reach equilibrium. Which of the following provides a correct comparison of the equilibrium concentrations of these chemical species and why? Okay, before we even switch slides, let's just talk about our K value. So, times 10 to the negative 11. Is that very big or is that very small? That is very small. So, when we're talking about big and small, we're kind of looking at that exponent right there. So that means that it is very small. And when we just learned that K is less than 1, that means that we will have mostly reactants at equilibrium. Okay, so that means that we're going to have more of the reactant side than the product side when we are at the equilibrium position. Okay, so we are figuring out which is a correct comparison based on that we have more reactants than we have products in our container at equilibrium. Okay, so looking at all of these comparisons, right away I know that B and C are both not going to be right because B and C have a reactant as being less than the products. And we just said there's going to be more reactants than products. The N2O5 is the product, remember? So that means that we won't have B or C as an option. Okay, then A versus D, they both have the product, the dinitrogen pentoxide, less than a reactant. But then we have to figure out which is better. So from there. So A says because a small K value indicates that the consumption of the reactants is favored at equilibrium. And D says because it indicates that the formation of products is not favored at equilibrium. So A is saying that it does want to consume the reactants, and D is saying that it does not want to form products. The correct answer is D, because since it is so small, we do not want to form products, meaning that we don't want to consume reactants. And so that's what's wrong with A, is the consumptions of the reactants, it won't happen. We won't be consuming the reactants, they will stay as is because we don't want to form products. Okay, so that's how you would indicate or use a comparison for our values of K. So moving on with our equilibrium expression and our equilibrium constant. In 7.3, when we learned how to write the equilibrium expression, we learned it for the forward reaction. So that's how we came up with our products of reactants equation. Now, what happens if you change the reaction somehow? Well, we can predict what will happen to the value of the equilibrium constant based on that change. So we have lots of different ways that we can predict, the first of which is just reversing the reaction. So if we do the backwards way, how you would solve for the new value of K would be you just inverse the original value of the K. Okay, so just whenever you notice that the reactants and products have switched, it's been reversed, take the inverse. When it's been multiplied by some factor, so you have the same equation in the same way, but it's multiplied by some value of n, then what you do is you would raise K to that power, so whatever it is. Now, you could multiply, you could divide. So if you have to divide, let's say like divide by 2, that's really meaning that you multiply by 1/2, right? So the 1/2 would be what you're raising the K to the power of. Okay, so that's how you would do that. If you have a Hess's law situation where reactions are being added together, then what happens is the result is the overall product, meaning we multiply the K's for each of the reactions that have been added together. So to find the K, you would multiply all of the K's together in that situation. You would still add the reactions together to make an overall reaction, but for the finding K, you would multiply. Okay, so, and any of these things that happen, so reversing it, taking the inverse, multiplying and taking it by that power, it all applies also to the Q expression for the reaction quotient. So we want to use some information from example 4 to calculate the value of K for the reverse reaction and for when we only form one ammonia molecule. So if you look back, example 4 is on page 6 in your note packet. That is for the synthesis of ammonia, which that equation is N2 plus 3H2 and 2NH3 is that reaction. And in example 4, we found that the K, the constant at equilibrium for this reaction, was 3.8 times 10 to the 4th. Okay, side note from 7.5. It's times 10 to the positive 4, so that means that the products are favored in this initial reaction. So we're going to have more products than reactants when you reach equilibrium. Okay, back to the problem at hand. So the first thing we want to do is for the reverse reaction. Okay, so for the reverse reaction, finding K, I just spelled reserved. Reversed. What we do is we just flip-flop it, right? Just like when we did Hess's law. So we have 2NH3 makes N2 plus 3H2. So this is the reaction we're talking about. We flipped around reactants and products. So then for the value of K, we said that when it's reversed, we will take, so that the K1 or the K with the apostrophe just means the new K kind of thing. It's a different than the original K. We have to take the inverse of K. So to find that, we would have to take 1 over 3.8 times 10 to the 4th. So our new value of K when it's reversed, when I inverse that, well, I got 2.6 times 10 to the -5th. Okay, so that would be how you would do it for inversing. Okay, now let's find it when there's only one ammonia molecule formed. So 1 ammonia. We currently have 2 ammonias created. So how we would get that to be 1 ammonia is we'd have to divide everything by 2. So our new reaction would be 1/2 N2. We don't have to flip it. It's not reversing, it's just reducing. Plus 3/2 H2 to create 1 NH3. Now we don't really like to have those fractions as coefficients, but because we only want 1 molecule formed, we have to have those fractions involved. Okay, so now to find the K here, we have to take K to the power that we multiplied by. So when we divided by 2, I said this before, that's like saying we multiplied by 1/2. So we're going to take the value, the original value of K to the 1/2 power, or take the square root of it. So that is 3.8 times 10 to the 4th to the 1/2 power, or square root, and I got that to be 195. So sticking with our 2 significant figures, you could say 2.0 times 10 to the 2nd would be a good value for that. Okay, so these are finishing the packet of notes that you already have, and look at the schedule for what homework problems from the textbook to do.